Hello everybody and welcome to our video on polar coordinates. So now we've talked about parametric equations and coordinate systems. Now we're going to talk about an alternative coordinate system called polar coordinates. So rather than using x and y axis coordinates, we will define a point's location by angle and a distance. So as a convention, when using polar coordinates, we will refer to the origin as the pole and the x-axis as the polar axis. So the point P is now defined by its distance r from the pole and the angle theta formed between the polar axis and the line between O and P, right? So this line from the origin to P is the line OP. The ordered pair r theta represents P, right? So what we're saying is, okay, why not, instead of giving an x and y coordinate, why not just say, hey, here's the direction you're going, given by the angle, and here's how far you have to go to get there. And that's r. Okay, so the standard convention is that positive angles of theta are measured counterclockwise from the polar axis. Additionally, if r is negative, then we consider the point P as pointing the opposite direction from theta. So the reason we consider counterclockwise angles to be positive is because we have the positive x-axis moving to the right. So if you imagine if you're aiming something in the positive direction, you have to rotate up from the x-axis to do it. And when you're rotating up, that rotation is counterclockwise. So here, if we rotate theta, but we go in the opposite direction, this point would have the angle theta, but the radius would be negative, right? So you'd have negative r. And of course, one more thing to notice here is that since this is exactly pi, it's a straight line, that the representation negative r theta is the same point as r theta plus pi, right? So if I went theta and then added pi to that angle and went the positive radius instead of the backwards radius, then you end up at the exact same place. So let's put this idea into practice a little bit. Plot the point whose polar coordinates are given, then find two other pairs of polar coordinates of this point, one with r greater than 0 and one with r less than 0. Okay, so let's start by drawing out our coordinates here. Now, since r is 1, I'm going to mark 1 in each direction here, just as like the start of a good habit, because no matter what direction we're going, if r is 1, that means it's going to be a distance of 1 from the origin. So if I just draw a lightly outlined circle with a radius of 1, then I know that this point has to land somewhere on that circle. Now, I'm also looking at 7 pi over 4, and 7 pi over 4 puts me down here, right? So this is 7 pi over 4. And so the intersection of these two things, of this angle 7 pi over 4 and 1, the radius 1, that's my point. Now it says, find two other pairs of polar coordinates of this point, one with r that's positive and one with r that's negative. So if I want the same distance, if I want the distance to still be going positive, I could find any angle that's coterminal with this. So what I mean, for example, is I could use this angle, which is negative 3 pi over 4. And I could write this point as 1, negative 3 pi over 4. And similarly, if I want the radius to be negative, if I want, or I should say r to be negative, right, then I want to be going in the opposite direction for my angle, right? And that would be pi over 4. So now if I'm pointed in the positive direction of pi over 4, right, I'm not going to end up at this point. But if I start at the angle pi over 4, but I go backwards from the origin, then I end up at the same point. So -1 pi over 4 is also a pair of a coordinate that ends at the same point. Okay, so there's 3 total ways to describe the same point. And that's one of the things that I think is really important to understand about polar coordinates, is that the polar coordinates for a point are not unique. You can have many ways of representing the same exact points. Okay, let's take a look at this other example. Here we've got r is -3 and theta is pi over 6. So since r is -3, I'm going to start by, again, drawing a circle with radius 3. And drawing the angle pi over 6, which is about here. But in this case, r is negative, so we've got to be going backwards from pi over 6. And so when we go backwards from pi over 6, we end up at this point that intersects between the radius of 3 and the angle pi over 6, but going in the negative direction from that angle. This is -3 pi over 6. Okay, let's find another representation with r negative first. So I think the easiest one to find is to do this angle, which is pi plus pi over 6, or 7 pi over 6. Or sorry, that would give me r as positive. My mistake. Well, we'll do that one first. If I go 7 pi over 6, then r would be +3, and our angle would be 7 pi over 6. Now, if I want to maintain that r is negative, I could rotate backwards all the way back around. That's one perfectly valid option. Why don't we do that one? So if I go from here to here, what angle is that? Well, it's 2 pi minus pi over 6. So it's 11 pi over 6. So that's the other option, is -3, 11 pi over 6. Okay, so that's enough of that. Let's move on. So what are the trigonometric relationships for polar and Cartesian coordinates? Well, it's basically the standard relationships that you're already used to. So if we've got an angle theta and we've got r, we can always draw a right triangle with the x-axis. So we know that cosine of theta is x over r, or in other words, x is r times cosine of theta. And we know that sine of theta is y over r. So in other words, y is equal to r times sine of theta. So if I know theta and I know r, I can easily find the Cartesian coordinates with that. Now we also know that for a right triangle, x squared plus y squared is r squared. So if we know x and y, we can solve for r quite easily. And if we know theta, we can find the slope, or y over x, right? Using tangent of theta. So, or I should say, if we have y over x, we can find tangent of theta, is one way of looking at it. That means that we can find theta by taking tangent inverse of y over x. So we can find r by using r equals the square root of x squared plus y squared. And we can find theta by using theta is tangent inverse of y over x. But with this next example, let's start with polar coordinates and find the equivalent Cartesian coordinates. Okay, so for A here, we've got r is -√2 and theta is 5 pi over 4. So x is just r, -√2, times cosine of 5 pi over 4. which is negative root 2 times negative root 2 over 2. Negative times negative is positive. That's positive 2 over 2, which is 1. And y is negative root 2 times sine of 5 pi over 4. That's also in the third quadrant, so also negative. We get the same thing. Okay. Now we'll do b. So same exact idea. X is 1 times cosine of 5 pi over 4. So that's just negative root 2 over 2. And y is 1 times sine of 5 pi over 4, which is also negative root 2 over 2. Now, we'll try to find the equivalent polar coordinates under a couple of assumptions that theta is between 0 and 2 pi, and we want a version for r greater than 0 or r less than 0. Well, since these are Cartesian coordinates, we can find r by taking x squared plus y squared is r squared. So r is the square root of 3 root 3 squared plus 3 squared. That's the square root of 9 times 3 plus 9. That's 27 plus 9 is 36. And the square root of 36 is 6. Now we know that tangent of theta is y over x. That's 3 over 3 root 3, which is 1 over root 3. Now, if I had angles that I didn't know the values for explicitly, like if I got a value here where it's like, I don't know what theta is, then you can make it theta equals tangent inverse of 1 over root 3 and use a calculator. But in this case, that isn't really necessary because I know that tangent is sine of theta over cosine of theta. And 1 over root 3 is the same thing as 1/2 divided by root 3 over 2. And I know that the angle that gives me 1/2 for sine and the square root of 3 over 2 for cosine is pi over 6. So that gives me my first version of the coordinates, which is 6 pi over 6. Now, it also wants us to find a version where r is negative. So if I just do a rough sketch here, if this is pi over 6, okay, if I want a negative version, I could just go out another pi. And so then I could write this as negative 6, 7 pi over 6. Okay, part B. We've got the point 1, negative 2. So r is the square root of 1 squared plus negative 2 squared. That's the square root of 5. And now this one doesn't work out so nicely. If I set up tangent of theta is negative 1/2, right? That's my y over x. I don't know any angles that give me 1/2 for tangent, but I can say that theta is tangent inverse of negative 1/2. Now, if you plug this into a calculator and you make sure that you're in radians mode, you will get approximately negative 0.4637. Now, the problem here is that we don't want a negative angle. We want a positive angle. So That's a little bit of a problem. Well, let's try to sketch this out and find the positive angle. So if this angle is the negative 0.4637 radians angle, then how do I find the positive version of that angle? Well, that's easy enough. I just take 2 pi and subtract that. And so I can set theta to be approximately 6.747. So the first version of the point that I would write out would be the square root of 5, 6.747. Now I also want a version of the angle where r is negative. So I want this one right here. Now keep in mind, this angle is also the 0.4637 from symmetry, right? And so this angle is just pi minus the 0.4637. So my second point would be negative root 5. And instead of 6.747, we get 3.605 when we subtract pi minus 0.4637. Okay, that's it for that one. So now let's try to take this information and see if we can start figuring out how to sketch curves in polar coordinates. Now some of them are pretty easy. So for example, sketch the curve r equals 3. Well, nothing to it. Let's draw our plane. You want the set of all points who have a radius of 3. A distance away from the origin of 3. That's a circle with radius 3. Done. Okay, example 5. Sketch the curve theta equals 7 pi over 4. Well, if I draw the angle 7 pi over 4, that puts me here. But the curve is just the set of all points that land on that angle. So here's all the points where r is positive, and here's all the points where r is negative. So of course we get a line for that. So one of the things this shows you is that in polar coordinates, the equation of a circle and the equation of a line are extremely simple. They are just constants, right? R equals 3, theta equals 7 pi over 4. And this should give you sort of a hint to where later in calculus you will really find polar coordinates useful, is that you can often take these very complicated Cartesian equations and reduce them to really simple polar expressions, and then that will allow you to do certain calculus work on them, like finding areas or volumes, etc., a lot easier because you'll have simpler functions to work with. Okay, now let's go ahead and graph something that's a little more complicated, though. So this says sketch the curve r equals cosine of 2 theta. So this is a little bit tricky, but if you are systematic in your approach to doing it, you won't have any issues. So we want to sketch the curve r equals cosine of 2 theta, and we want to do something a little bit more wise than just plotting points, but there is some degree to which we have to plot points, but we don't want to plot a million points. We want to plot sort of just enough points. And so what I want to do is figure out key values for this thing. And I know that cosine has a minimum value of -1, a maximum value of 1, and right in between those two is 0. So what I want to look at is when is this function equal to these values. So I'm going to start with 1, and I'm starting with 1 because when theta is 0, cosine is 1. So that seems like the natural starting point. So 2 theta is my input. So when that thing is 0, when 2 theta is 0, I get cosine of 0 is 1. But I also get 0 for cosine. I said 0 for cosine. I also get 1 for cosine at 2 pi, at 4 pi, at 6 pi, every 2 pi multiple, right? And of course, all the negative ones as well. But for sketching, we won't need to really draw the negative angles for these. Now I divide all of these angles by 2, and I see that we get when theta is 0 or pi or 2 pi or 3 pi, etc., that's when r will be 1. And what about when r will be 0? Well, that would be when my angle inside the function is pi over 2, because cosine of pi over 2 is 0. And also 3 pi over 2. And also 5 pi over 2. Every additional pi that I add to this gets cosine to be 0 again. So now if I divide all of those by 2, I get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, etc. And now, when r is negative 1, when does that happen? Well, that happens when 2 theta is pi, 3 pi, 5 pi, 7 pi. I don't really need to write out as many as I am. I'm just kind of trying to be super thorough. I divide all those by 2. And now what we're going to do is sketch these key values for the curve. Right, the values when r is 1, 0, or negative 1 by looking at the angles and starting with 0 and moving up. But before I do that, I know that the largest radius I have to deal with, the largest value for r, is 1. So I'm going to draw a circle with radius 1, a nice little dotted outline here. And now I'm going to draw dotted lines for the angles that I'm going to be drawing, right? So we're drawing 0. I'll leave out the angles on the quadrants, but then we're going to be drawing pi over 4. And we're going to need 3 pi over 4. And 5 pi over 4. And 7 pi over 4. Okay, so when we look at angle 0, so we're going to go through order and kind of cross off the angles as we deal with them. When we look at theta is 0, r should be 1. So when I'm looking at this angle, r is 1. And now, when I go to theta is pi over 4, my r should be 0. So from here to here, my radius has to shrink down to 0. Now here's where it gets tricky. Because when theta is pi over 2, so now I'm looking up here at theta is pi over 2, but r is negative 1. So I'm actually going the opposite direction. And now I'm going from 0, and as I rotate through here, I'm doing a mirror image of this segment, right? This is the segment we're looking at of angles, and so I'm looking at the opposite angles here, and it's rotating through there. Now we go to pi over 2. And, we just did pi over 2. Now we go to 3 pi over 4. That's my next angle. So at 3 pi over 4, r is 0 again. So when I correspond to this angle, r goes from being negative up to 0 when it lines up with this angle here. All right, so here, now we were looking at this triangle, or this segment, I should say, but the r values were still negative, so we were in the mirrored section. Now I'm going to go ahead and just erase those. Those were for illustrative purposes. Now we go to theta is pi, and r is 1 again. So it's going to rotate out to here. And then when we get to 5 pi over 4, r is going to be 0 again. And now when we get to 3 pi over 2, r is negative. So now we're looking at the angle down here, but r is negative, so it's going to rotate up to here. And now 7 pi over 4 is going to give me 0 again. So I rotate through here until I line up with this angle 7 pi over 4. And then at 2 pi, somehow I forgot to cross off my pi. At 2 pi, I end up back at a radius of 1. And now it should be clear that since you ended at the same point you started, as we go through these angles, we're going to rotate through the same exact pattern. So we don't have to draw anything else there. We've drawn the whole picture. So we often call this like a four-leafed rose, would be the typical name for it. Now notice here, we had cosine of 2 theta. We ended up with 4 leaves. Now you will be tempted to overgeneralize that, and maybe you'll notice a pattern with that in general for even numbers times theta, but it's not a very helpful pattern, because if you want to draw these things properly, you have to go through this process anyways. So just trying to like memorize, oh, it should have this many leaves or etc., it's not going to help you too much when it comes to actually sketching out these pictures. So let's do a similar one. Sketch the curve y equals sine of 3 theta. So we're going to go through the same thought process, right? I want to know the key values for sine. When is sine 1, 0, and negative 1? But I'm going to start with when r is 0 here, because when theta is 0, sine of 3 theta will be 0. So again, I still want to start with theta being 0. So r is 0 when 3 theta is 0. But when else is sine 0? Well, at pi, and 2 pi, and 3 pi, and so forth. And so if I divide everything by 3, I get theta is 0, pi thirds, 2 pi thirds, 3 pi over 3, which is pi, so forth and so on. And now we'll look at r as 1. And that occurs when the input is pi over 2. So 3 theta is pi over 2. But it also happens when you go a full circle around and add 2 pi to that. So that's 5 pi over 2 and 9 pi over 2 and 13 pi over 2. So theta is pi over 6, 5 pi over 6, 9 pi over 6, which is 3 pi halves, and 13 pi over 6. And r is negative 1 when 3 theta is 3 pi over 2, or 7 pi over 2, or 11 pi over 2, or 15 pi over 2. And so theta is 3 pi over 2 times 3, which is just pi over 2, or 7 pi over 6, or 11 pi over 6, or 15 pi over 6, which is also 5 pi over 2. Or, wait, hold on. 5 pi over 2. There we go. Got to make sure I don't do something silly. Okay, and now we're going to do basically the same thing. I'm going to sketch a plane here. I'm going to mark out my radius of 1 by drawing a little dotted circle here. And I'm going to start marking angles, right? We need pi over 6, pi over 3. We're going to need, let's see, 2 pi thirds, 5 pi over 6. We got 7 pi over 6. We've got, that's going to be 4 pi thirds. Okay, I don't need to mark the rest of them. I think that's enough for us to work it out. Okay, and we'll start. When theta is 0, r is 0. So I draw my point at 0, 0. When theta is pi over 6, r is 1. So I rotate out from that angle of 0 to pi over 6, and it lengthens to a radius of 1. And then next would be pi thirds, where r is 0 again, so it comes back down. And now I'm looking at this angle range, but r is going to be negative, right? When theta is pi over 2, r is negative 1. So I end up down here, and I'm rotating through the opposite angles of this sector here. So I rotate through this way. And now I'm going to look at 2 pi thirds. And so 2 pi thirds, where's 2 pi thirds? R is 0, so I come back to here. And now I'm looking at 5 pi over 6. R is 1, so I go out to here. And then I look at pi. And r is 0 again. Now look at what happens next. When I go out to 7 pi over 6, I'm going to get r is negative 1. So I'm going to be looking here, but that's going to put my point over here. So you see, I'm actually going to repeat these 3 loops already, even though I've only gone from 0 to pi. So what we see is that in this case, we actually have the same number of petals as that multiple of theta here. Whereas for cosine of 2 theta, we had double the number of petals. But again, don't worry too much about that relationship, because when it comes to drawing them, if you want your drawings to be accurate and useful, you're going to have to go through this process anyways. Okay, example 8. Identify the curve by finding a Cartesian equation for it. Okay, so we've got theta is pi over 3. Now I could try to work through some process to figure out what this curve is and substitute and yada, yada, yada. Or I can draw the angle pi over 3. Realize that this is the straight line passing through 0, 0. And the slope of this line is y over x, right? So in other words, tangent of theta. So this is y equals mx. The intercept is 0. And m is tangent of theta, which is just tangent of pi thirds. That's sine over cosine. Sine of pi thirds is the square root of 3 over 2. Cosine is 1/2, and that simplifies to root 3. So this is just radical 3x. Okay, example 9. Graph r equals 1 plus 2 cosine of theta. Well, we want to go through the same sort of thought process as before, but it's a little bit more complicated. So here, we're going to look at when cosine of theta is 1, what does that make r? Well, then r would be 1 plus 2 times 1, which is 3. So we ask ourselves, when is cosine 1? Well, that's going to be when theta is 0, or 2 pi, or 4 pi, etc. And when cosine of theta is 0, what happens to r? Well, we get 1 plus 0 is 1. And that's going to happen when theta is 0, or is pi, 3 pi, 5 pi. Sorry, pi over 2, 3 pi over 2, 5 pi over 2 was what I meant to write. Okay. Now, what happens when cosine of theta is -1? Well, then r will be 1 minus 2, which is -1. So theta, when is that going to happen? When theta is pi, 3 pi, 5 pi, etc. So our largest value of r is occurring at r is 3. So I'm going to go out 3. And we'll dot a nice little circle of radius 3 out there. And our shortest value for r is 1 or -1. Either way, we'll use a circle of radius 1 for that part. Now, this should give us enough information, but keep in mind, you may, as you're drawing these things, figure out that, oh, you know what, between such and such angle, I need a better idea of what's happening there. So you can always check an extra point to figure out more details if you feel that you need them. But in this case, if we start at 0, r is 3 when the angle is 0, so I plot that point there. And when I go to theta is pi over 2, r will be 1. So from here to here, it goes like that. Now, when I get to the angle pi, r is going to be -1. And that's where it becomes a little bit tricky, because how did I get from there, from this positive radius to -1? Like, which way did it rotate? So we can always pick an extra angle. That's exactly what I was mentioning before. So between pi over 2 and pi is 3 pi over 4. So that seems like an obvious place to check. Or I could be more specific. I could say, if you don't want to check theta is 3 pi over 4, you could say, well, when is r 0? Because if I know that it has to pass through 0 for some angle to become negative, that might be worth checking. So maybe I'll try that instead. Let's see when r is 0. Well, r is 0 when 1 plus 2 cosine of theta is 0. So that's when cosine of theta is -1/2. And that's when theta is, let's see, 2 pi thirds? Yes, 2 pi thirds. So that tells me if I mark the angle 2 pi thirds, that my graph needs to go down to 0 in a line with that angle. And now it's going to rotate out down to -1 when I get to pi. And then it's going to go back to 0. Where? Well, not only at 2 pi thirds, but also at 4 pi thirds. And then after 4 pi thirds, when we get to 3 pi over 2, r will be 1 again. So I go out to that distance of 1. And then when we get to 2 pi, r will be 3. So we usually call shapes like this something like a cardioid because it looks kind of like a heart. All right. Now that's not a perfect cardioid pattern. A lot of cardioids will actually look exactly like this, but this one's similar enough that I think it deserves the same title. All right, that's it for that one. Let's take a look at example 10 here. This is going to be the last one we draw for now. Now this one, we don't have these nice sort of repeating behavior for sine and cosine that we can use to figure out what this graph is doing. So we kind of have to brute force it, but we still get to use a little bit of what we know about logarithms. So for example, we know that as theta goes to infinity, ln of theta goes to infinity. So we know that the radius is going to get longer the bigger I make the angle. Now we can start by plotting a few points, and we want to plot points that are easy. So when I check out ln of 1, well, I know ln of 1 is 0. So when theta is 1, r is 0. And ln of e, well, e is roughly 2.7-ish. And ln of e is 1. And I'm going to also use ln of e squared, which is 2, right? These are inverse functions, so ln of e squared is 2. And then we're going to try to plot this stuff. Now, remember, pi is roughly 3.14. So if my theta is 1, that's pretty close to 1/3 of pi. It's not exactly 1/3 of pi, but it's pretty close. And if I look at e is roughly 2.7, so that's a little bit less than pi. So that's going to be something like this. But e squared is about 7.4, which is more than 2 pi. So that's going to put it roughly over in this area. And now we've got a radius of 0, 1, and 2, so we're going to go out to 2 and draw our little circles. Okay, and now we'll start plotting. So when theta is 1, r is 0. As it rotates out to theta is e, we should get r is 1. So it should kind of rotate out this way. And then it keeps getting bigger to here. So it's going to keep rotating this way. And we can kind of predict that the rest of the graph is going to do something like that. Okay. So now let's talk about a little bit of calculus involving polar coordinates. So first, we'll start by taking a look at tangents. Okay, so notice that r is a function of theta, x is r times cosine of theta, and y is r times sine of theta. And we know from parametric equations that dy dx is dy d theta divided by dx d theta, right? That's the same thing. So we can solve for dy d theta as dr d theta times sine of theta plus r cosine of theta. That's just the product rule here, right? Look, y is r times sine of theta. That's r prime times sine of theta plus r times sine of theta prime, right? Just the product rule on y. And dx d theta is dr d theta cosine of theta minus r sine of theta. So again, same thing here, right? The derivative of r times cosine of theta minus r times the derivative times sine of theta, because the derivative of cosine is negative sine of theta. And so dy dx is just the quotient of those two things. We just divide them. Now, one thing to mention here is that if we are looking for tangents at the pole, in other words, when the radius is 0, then this thing simplifies because the second term on the top and bottom disappears, and then the dr d theta can cancel at that point, and you get left with sine of theta over cosine of theta, which is just tangent of theta. Okay, so let's take a look at this example. Find the slope of the tangent line to the given polar curve at the point specified by the value of theta. So the first thing we need to find is dy dx. So we've got dr d theta times sine of theta plus r cosine of theta over dr d theta times cosine of theta minus r times sine of theta. So first thing I need to figure out is what's dr d theta before I can compute any of this. Well, the derivative of 2 is 0. The derivative of sine is cosine, so this is negative cosine of theta. So when I substitute r and dr d theta in place, I get negative cosine of theta, sine of theta, plus 2 minus sine of theta times cosine of theta over negative cosine of theta times cosine of theta minus 2 minus sine of theta times sine of theta. Okay, so up top here, we'll leave the first term alone. Now we'll distribute this cosine of theta, so we get 2 cosine of theta minus cosine of theta sine of theta over. Down here we get negative cosine squared of theta. We're going to distribute this sine, and since there's a negative in front here, the first term will become negative 2 sine of theta. And the second term was negative, but the second negative will make it positive, so that becomes plus sine squared of theta. Okay, and I'll just clean this up slightly. We've got negative cosine theta sine theta. Negative cosine theta sine theta, that's negative 2 cosine theta sine theta. Plus 2 cosine of theta over negative cosine squared of theta minus 2 sine of theta plus sine squared of theta. All right. So now we need to evaluate this thing at pi over 3. So everything is just cosine and sine. So I'm going to evaluate those off to the side first, right? Cosine of pi over 3. What's cosine of pi over 3? Oh, that's 1/2. What's sine of pi over 3? Oh, that's the square root of 3 over 2. And so when I evaluate dy dx at, or dy, at theta equals pi over 3, we get negative 2 times the square root of 3 over, or sorry, 1/2. Already, I'm writing stuff wrong. 1/2 cosine of theta times sine of theta, that's the square root of 3 over 2, plus 2 times cosine of theta, which is the 1/2, over negative 1/2 squared minus 2 times the square root of 3 over 2, plus sine squared of theta, which is the square root of 3 over 2 squared. Okay, 2 times 1/2 is 1, so this first term becomes negative root 3 over 2. And 2 times 1/2 is 1. Down here we've got a negative 1/4. 2 over 2 cancels, that's negative root 3. And this is root 3 squared, which is 3 over 4. Okay, so this is basically an answer. It's fine. But we can simplify it a little bit, and the quickest and easiest way to do that is we notice all of our denominators in our big denominator, all of these fractions have a denominator of 4 or 1, right? So if I just multiply by 4, that'll cancel all of those denominators. And so I'll do the same thing up top. And we'll see that we get negative root 3 over 2 times 4 is negative 2 root 3 plus the 4 times 1 over negative 1/4, which is times 4, which is negative 1, minus root 3 plus 3. And the last thing I'll do here, say negative 1 plus 3 is 2. So over 2 minus root 3. Okay, so that would be the slope for our tangent line of that curve at that point. Okay, that's it for that example. We have one more example to take a look at, and then we'll be done with our video on polar coordinates. Example 12, find the points of the given curve where the tangent line is horizontal or vertical. So, quick thing to understand here is that if a line is vertical, that means the change in y is 0. So we don't have to look at dy dx, we can just look at dy d theta. And if a line is horizontal, we don't need to look at dy dx either, we can just look at dx d theta. Right, because the change in x is 0. X, I totally put those backwards. Let's try that again. Dy d theta is when it's horizontal, and dx d theta is when it is vertical, right? When it's vertical, the x value is not changing. When it's horizontal, the y value is not changing. Okay, so let's take a look at that. We know that dy d theta, well, first of all, y is r times sine of theta. So if you forget what the formulas for dy dx or dy d theta or dx d theta are, just as long as you know that y is r times sine of theta, you can just get those formulas by doing the product rule. And I go, okay, well, that's dr d theta times sine of theta. And then I'm going to get r times the derivative of sine, right, plus r times cosine of theta. And so if I want to see when is dy d theta 0, well, first I got to substitute my values in here. If r is e to the theta, well, that's pretty easy. Dr d theta is also e to the theta. So this is e to the theta times sine of theta plus e to the theta times cosine of theta. And so I can factor out e to the theta times sine of theta plus cosine of theta. Now, if I want this thing to be 0, I just set it equal to 0. But e to the theta can't be 0. So I only have to worry about sine and cosine. If I subtract cosine, that gives me sine of theta is negative cosine of theta. And then if I divide cosine, I get tangent of theta is negative 1. And so whenever theta is negative pi over 4 plus any multiple of pi. Remember, the period for tangent is pi, so it repeats its values every time you add a multiple of pi. And so r, the corresponding r values are e to the negative pi over 4 plus pi n. Now, to be clear, for each point, it has to be the same n value, right? This is a whole bunch of points that all have that tangent line being, we're talking dy d theta is 0 here, right? So we're talking about the horizontal case, right? So we have a whole bunch of points where this curve is horizontal, and each point corresponds to the pair with an individual n value. And n here is an integer like 1, 2, 3, -1, -2, -3, 0, obviously. Okay, and now let's consider the vertical case. So vertical case would be when dx d theta is 0. All right, well, what's dx d theta? Well, x is r times cosine of theta. So dx d theta is dr d theta times cosine of theta minus r times sine of theta. That's e to the theta cosine of theta minus e to the theta sine of theta. Factor out the e to the theta, get cosine of theta minus sine of theta, and set it equal to 0. And again, e to the theta can't be 0, so in this case, we get that cosine of theta minus sine of theta is 0, and so cosine of theta is sine of theta. So if I divide by cosine, I get tangent of theta is 1. And so theta is pi over 4 plus any integer multiple of pi, and r is e to the pi over 4 plus any integer multiple of pi. Okay, that's it. We made it through this video. Thank you for watching.